The probability that Chadwick will win is set at 41%, which means that the probability that he loses is 1 minus 41%, or 100 minus 41%, which is 0.59. The probability that Viola is going to win is 0.55, and the probability that she loses is what's left of the 100%, and that's 0.45. So if you're going to find the probability that they both win, you have to take the two probabilities, one that Chadwick wins and the other that Viola wins, and multiply them together. And when you do that, you get 0.2255. And similarly, the way you go about finding the probability that neither of them wins is to take the two probabilities that they are going to lose, that each of them is going to lose, and multiply them together, 0.59 times 0.45, and you get 0.2655. In order to find the probability that only one of them wins, the way to do that is to think of the two possible ways that can happen. One is that Chadwick wins and Viola loses, and the other is that Viola wins and Chadwick loses. And you need to find those two probabilities and then add them together. So it's a process of multiplying and then adding. To find the first part, you take the probability that Chadwick wins and multiply it by the probability that Viola loses. You get 0.1845. And then you take the probability that Chadwick loses and the probability that Viola wins, and you multiply those together, you get 0.3245. And when you add those together, you get 0.5090. And at this point, I wasn't sure whether all of that was reasonable or not. So what I did was I took the three probabilities, since I thought about it and realized that this pretty much is the only group of things that can happen. There's nothing else left out of this. Either they both win, or they both lose, or one of them wins. So if I add those probabilities up, they should equal 1. Or if I add them up as percentages, they should equal 100%. And so I did that, and they did. So I was fairly confident that I had the right numbers. Here's the problem. You've got a classroom, and of course, this is a real life situation where as soon as the kids walk into the room, they rush to get to the front seats and place themselves down. So the question is, what's the probability that they randomly wind up boy, girl, boy, girl, boy, girl, boy, girl? And there are two ways that this can happen, but we'll get to that in a minute. Step one is you have to figure out the number of possible outcomes. How many different ways can 14 children sit in 5 seats rather, where order makes a difference? Okay, so the way you figure that out is just simply by saying there are 14 kids that can sit in seat 1, 13 in seat 2, 12 in seat 3, 11 in seat 4, 10 in seat 5. Multiply them together, you get 240, 240,240 different ways, which is a staggering number when you think, well, there are only 14 kids in the room. Yep, that's it. So this notation means the number of possible results is 240,240. Step two is to figure out the number of favorable results. And that doesn't mean necessarily that it's good or better that the kids are sitting in alternating seats. It simply means that these are the results that you are looking for. They're the results that fit the criteria you've set up in advance. How many different ways can the boys and girls alternate in the front row? And there are two ways this can happen. One is that the boy could be first. And that becomes, there are 8 ways that can happen, 8 different boys that could sit here, and 6 girls that could sit in the next seat. By the time you get to the third seat, there are only 7 left, since one boy is already sitting over here. And there are 5 girls left for the fourth seat for the same reason, and 6 boys left to fill in the last seat. And if you multiply those together, you get 10,080 different ways that you can fill the front row with alternating kids if the first seat has a boy in it. And you notice the reason that this makes difference is that you've actually chosen 3 boys out of the 8 that are there, and 2 girls out of the 6. If a girl sits in the front seat, then it's going to flip. In other words, it's going to be, you're going to choose 3 girls and only 2 boys. So the number of possible options here are different. You've got a girl sitting in the front seat, so there are 6 kids that can sit there, 8 boys to choose for the first boy seat, and then it goes 5 times 7 times 4, which is 6,720. So of all the different ways this can happen, it's these 2 added together. So the favorable results are 16,800. Step 3 is to actually calculate the probability. And the way to do that is to take the number of favorable results and divide it by the number of possible results. And that would be 6,800, which comes from here, divided by 240,240, which came from up here. And that comes out to be this lengthy number in the calculator, which rounds to 0.070. Last period, a student actually pointed out that there was a different way to do it. What he said was he actually found the probabilities of each of these things, each of these 10 things here, and used those instead of the big numbers, because he said when you did it, you still wound up with the same numbers, except that before you actually calculated them, you could cancel them. So he showed a bunch of different ways to cancel these out or reduce the fraction. And he got 6 over 143 for this. He got 4 over 143 for that. And when he added them together, he got the same answer. So this would be the probability for boy first, and this would be the probability for girl first. So in this particular situation, we're talking about testing students for COVID, and we are assuming that the probability of testing positive is 5%. And this is a situation where what you're doing is running the same experiment over and over, right? Testing for COVID. And in this situation, there are only 2 possible outcomes. You're either positive or you're negative. So when you have this situation where you're running the same experiment over and over, and there are only 2 possible outcomes, that is when you use the binomial probability distribution. Okay. And what that means is, okay, probability of getting a negative test, which would mean you have COVID, is A. I'm sorry, you don't have COVID is A. Probability of negative is A. The probability of positive, which means you do have COVID, is B. And N is the number of times the experiment is run. So taking a look here, if you add the 2 probabilities together, of course, they equal 1. If you raise it to the 10th power, it still equals 1. So the entire, the probability, the sum of the entire range of probabilities is equal to 1. If you expand this, you get this. And what this actually says, right, for each one of these terms, you have the probability that there will be as many of each result as the exponent for that particular probability. So here, probability is for the negative result. The 10 means this is the probability of having 10 negative results and no positive results. Here, we're talking about 9 negative results and 1 positive result. And it turns out there are 10 different ways for that to happen. What does that mean? Well, think about it. You've got 10 people. The first one could be the positive person. The second one could be the positive person. The third one could be the positive person. Each one of those is a different situation. So we have to include it here, which is why we multiply by 10, because there are 10 different ways that can happen. There are 45 different ways that you could have 8 people without COVID and 2 people with it. And that's not something you need to be able to do in your head. In fact, what we're talking about is 10 people, and you have to choose 2 to have COVID, and you don't care what order they're in. So that's a combination. It's 10 choose 2, and that turns out to be 45. So there are 45 different ways for this to happen. And again, all the way through, that's what this is. 210 times the probability that you're going to have 4 people who are negative and 6 people who are positive, all the way down the line. So the thing to do now is to look and say, well, which ones are the favorable results? The favorable results are these guys over here, because you're looking for no more than 2, which means not 3, not 4, not 5, maybe 2, maybe 1, maybe 0. These 3 would be not more than 2. Right? Nobody has it, 1 person has it, 2 people have it, and no more. That's that. So what we have to do is find each one of these probabilities and then add them together. So here is each one of those probabilities added together. Right? The probability of not having COVID is 0.95. So you raise that to the 10th for the first one. You raise it to the 9th for the second one, and represent the 10th person with 0.05, because that's the probability that somebody will have it. And you multiply it by 10, because that's how many ways there are to have that happen. In the third one, you've got 45. You've got 8 people who tested negative and 2 people who tested positive. When you multiply those together, you get the third term here. And then when you add the 3 terms together, you get this long number, which rounds to 0.988. And that is the probability that no more than 2 people will test positive. So for this problem, you got this amusement park ride, and there are all these different outcomes. Each outcome has a specific return to it. There's a cost to enter the game. And basically what you need to do is to figure out all of these things. If you actually get 3 Frisbees into the clown's mouth, well, it's going to cost you $4 to play the game. So that's a negative to start with, but you're going to win $8. So the net result is that you've won $4. The probability of this happening is 0.6 cubed, which means there is 0.216 probability of this. And when you multiply this by the $4, you get your expected value of that, which would be 0.864, 86.4 cents. When you do the same thing with 2 Frisbees, what's the achievement? The achievement is I got 2 Frisbees into the mouth. And again, you win $6, but it costs you $4. So your net result is a positive $2. The probability of this happening is 3 times 0.6 squared times 0.4. What we're talking about here is 3 different ways that you can get 2 Frisbees into the clown's mouth, or might even be easier to think of it as 3 different ways you could miss. You could miss with the first one, you could miss with the second one, or you could miss with the third one. And missing 1 is the same as hitting 2. So when you multiply those numbers together, you get the probability that you are going to get 2 Frisbees into the clown's mouth and 1 will just hit him in the nose. When you take this number and multiply it by the net result over here, you get the expected value, which coincidentally is the same. Okay, that's just a coincidence. The probability of getting 1 Frisbee in and missing the other 2, remember there are 3 ways to do that as well. You could hit it with the first one, the second one, or the third one. The result is you get a $2 prize, but it costs you $4 to get in, so your net is a loss of $2. When you multiply that by 0.288, you get the expectation value that goes with that one. And then assuming you get 0 Frisbees, well, if you get none of them in, you win nothing. You spend $4 on the game, your net loss is $4. The probability of that happening is 0.4, 0.4, 0.4, right? The probability of missing each of the 3 multiplied together, that turns out to be 0.064. And then you multiply that by the net loss and get that number. Then when you add these numbers up, you get the expected value, which turns out to be a positive 89.6. In order to check how you're doing, sort of a mid-course check, if you add these probabilities together, since these are the only ways that this can turn out, right? I mean, you've covered it all. You get 3 in, 2 in, 1 in, or none in. That's it. These have to add up to 1. So at the point where you've got all the probabilities laid out, that would be a good time to stop and check to make sure that you haven't made a mistake somewhere along the line. Now, the question also asks, is this a good game to play? Should we play this a lot? From a statistical point of view, yeah, absolutely. This is a game you should play over and over for the long haul, because you'll win the equivalent of an average 89.6 cents every time you play the game. The downside of this game, when you actually stop to think about it, is you're not going to get paid in pennies. You're going to get paid in stuffed bears. So from a practical point of view, it's probably not a good idea to play this game a lot unless you have some particular use for a lot of stuffed bears.